Right, we are kicking off Chapter 8 with Lesson 8.2 is where we're going to begin. Chapter 8 is all about the wonderful world of right triangles. I would say probably out of the entire course of geometry, this is probably the most important chapter for you as far as moving forward in math. So much of what you're going to see in future math revolves around right triangles. Especially trigonometry. It's all designed around right triangles. So super important chapter. So make sure you follow along really well with each lesson because, like I said, it will have a really big impact on some future math for you. So here's where this begins, is with something we call Pythagorean theorem. So we got to understand a couple things first of all about right triangles. So let's look at this diagram that you see over here on the right. So obviously it's called a right triangle because there is a right angle in it, right, which is 90 degrees. So one thing to keep in mind, if this is 90 degrees, and we know that all three of these angles must add to 180, well, if this is 90, what does that tell you about angle A and angle B? Right? They must be the other 90 degrees of this triangle. Right? Since 90 plus 90 equals 180. So, for example, let's just say this one was 40. What would that make angle B? Right? He would have to be 50, right? Because these guys will always add to 90 degrees when you have a right triangle. As far as looking at the side lengths, you see that there are two segments right here that form the right angle. Those two segments are called the legs of the right triangle. So those are the two legs. The segment that is across from the 90 degrees is called your hypotenuse. Right? So here's something you could jot down in your notes, but so we're going to point to this guy and to this guy. So again, those are called the legs. Are those two, and then C, side C, is called the hypotenuse. The hypotenuse is always the largest side of a right triangle. And it's always directly across from the right angle. So when we do Pythagorean theorem, right, it's just basically a formula. It looks like this. It's called a squared plus b squared equals c squared. So in other words, if you actually put some real numbers in for these guys, if I were to square this, and square this, right, then this plus this would equal this guy. So that's what we're seeing. It's really just a formula, and we're going to be solving that formula. So we're going to start out with one that we see over here on the left. So for the first example, notice that they are telling us this leg is 12. They're telling us the hypotenuse is 13. And we're trying to find our missing leg that's over here on the left. So this is the formula for A, B, and C. Keep in mind, as far as the two legs go, it doesn't really matter which of these you call A and which one you call B. What matters most is that we call the hypotenuse C, because he's the one that has to be by himself when we plug into this formula. So what they did was they said, okay, let's take our A squared. We got 12 going in for b squared, and then we got 13 going in for c squared. And it looks like they messed up on the little 2 right here. I think this is supposed to be 13 squared, not 132. I think that 2 got misplaced. I think it should look like this. That would make more sense. So we're plugging those in. All we got to do is simplify it. So we know that 12 squared is 144. We know that 13 squared is 169. And then we're just going to solve this equation to get A by itself. So we would start by subtracting 144 from both sides. And then here's kind of the final step, and this is an important final step. But how do we get rid of an exponent like this? Right? We know that when we solve an equation, the goal is to always do the opposite of whatever operation you see. Like when this said plus 144, well, what did we do? We subtracted 144. We did the opposite. So what is the opposite of squaring A? Well, the opposite of the exponent would be a radical, right? So we're going to take the square root of both sides of this equation, because the square root and the little 2 here cancel each other out. And so you're left with just a. On the right side, I'm now looking at the square root of 25, which is 5. And that's it. We have our missing side length over there. So really, once we plug these into our formula, it's just a matter of solving the equation. Right? Not much more than that. So let's peek at one more of these, and we're going to try some together. So if you go over to this side, we have these guys can be A and B. Again, it really doesn't matter which one is A and which one is B, as long as you recognize that these are the two legs, and they're going to go here and here, and then the hypotenuse is what's going to go over here. So we're going to put 20 in for A, we're going to put 30 in for B, so here's this setup. And then just like the previous one, we just have to simplify this. So we're looking at 20 squared, which is 400. I'm looking at 30 squared, which is 900. And if I add those together, I get this stage right here. And remember what we just previously did, is this is where you square root the equation so that you can get C by itself. Right, and so that's where we get this statement. Now we can leave it like this. We can put it into our calculator and get a decimal. We can also simplify square roots, right? And that's something else that we're going to work on. So this could actually be written as 10 root 13. So there's like 3 different ways we could write this answer, right, when we get these. And so we'll talk more about how you'll know what to do. It's just going to be really just a matter of following directions. So if the directions tell you to round it to like the nearest tenth, then we'll plug it into a calculator. If it says to simplify your radical, then we would want to write it this way. So let's take a look at a few of these guys together. So we're going to plug these into our Pythagorean theorem. So again, we got our A, we got our B, and we have our C. Right? And again, I know that these are the values for A and B because they're the two legs, they're the two sides that form the right angle. And then the one across from the right angle is your C value. So I know that's my C value right there. So we're going to say a little A squared plus B squared equals C squared. So there's our setup, and we're just going to simplify to get X by itself. So I know 3 squared is 9. Oops, should be an equal sign. So that puts me here. So 18. So that puts us here, and then the final step is where we square root both sides so that I can get X by itself. So guys, remember on this, right, what happens on the reason we're doing this is because the square root and the square cancel each other out. And so that just gives you X. And so we can leave this as the square root of 18. That would be an option. If the directions say to round your answer to the nearest tenth, then we could go into a calculator and we would write it as 4.2. So that's an option. We can also simplify our radical, and this is something we'll definitely be spending time on, but if I look at the square root of 18, remember the way that we can view this, right, is I know the square root of 18 is 2 times 9, and I know 9 is 3 times 3. All right, so as I look at my what we call our prime factors of 18, which are 2, 3, and 3, right? Remember, a square root means you have a number times itself. That's why if I were to say, what's the square root of 4? You would say 2, because 2 times 2 is 4. So anytime you have a number times itself, that's the guy that gets to leave the radical. And if there's any numbers that don't have a partner, then they got to stay underneath the radical. So if the direction said to simplify your radical, then this is the way that we would want to write it. All right, let's jump over to this guy here. Again, these guys are A and B. It doesn't matter which one is which, as long as I recognize that my C value is across from the right angle. So I'm going to say, here's an A squared plus B squared equals C squared. And then we're just going to simplify that to get X by itself. So I know 9 squared is 81. 15 squared would be 225. And if we subtract 81 from both sides, let's see, what's 225 minus 81? So we would get 144. And again, here's that key step. There, I get rid of the exponent by taking the square root of both sides of that equation. That's what gets x by itself. And on this side, now we have a perfect square, right? The square root of 144 is 12. So really only one way to write that. So if it's a perfect square, we definitely want to make sure that we write it as an integer like this. All right, so here's one of the ways that this idea can now get used within another geometric shape. So you'll see on this one we now have a rectangle, right? So in a rectangle, of course, all the angles are 90 degrees. So that's a right angle, that's a right angle, right angle, right angle. So in a rectangle, you get 4 angles that are 90 degrees. When you draw in the diagonal of that rectangle, right, you can now see that we've now created a right triangle within the rectangle. And we're going to solve it the same way we did all the others. So as I look at just the right triangle, where I see the 16, the 33, and the x, again, we can now plug those into Pythagorean theorem. Those guys would have to be the 2 legs because they form the right angle. Here's my hypotenuse is the diagonal. So we're just simply going to say we got a squared plus b squared equals c squared. So just identifying right triangles within other shapes is going to be a big part of this, because you'll find that within a lot of shapes, there's a lot of right triangles that are formed within other shapes. So if we did 16 squared, we get 256. If I did 33 squared, I get 1089. And I'm just trying to get x by itself, so I'm going to add those two together and get 1345. And then here comes that super important step where I'm going to square root both sides so that I can get x by itself. So square root of 1345, let's put that in here. So if we wanted to round that to the nearest tenth, then we're going to say 36.7. And there's our value for x. So if we go on to this shape over here, this is another type of parallelogram. We call this a rhombus. In a rhombus, and we're not going through all the details of this shape right now, but in a rhombus, you'll notice that the 2 diagonals, so here's a diagonal, and here's a diagonal, but in a rhombus, the 2 diagonals are perpendicular to each other. So they create this right angle right here. Well, now I'm looking at 4 right triangles, right? That's a right triangle, so is that one, so is that one, and so is that one. So in a rhombus, you actually get 4 right triangles when you draw the diagonals. So, but anyway, all we want to focus in on is one of those right triangles. So here are my 2 legs. They are x and 11. Hypotenuse is 28. So if we go into our Pythagorean theorem, here's my a squared plus b squared equals c squared. And we're just going to clean that up, get x by itself. So I know 11 squared is 121. Oops. Let's see, 28 squared is going to be 784. Subtract 121 from both sides. We get 663. And then here's another one that's not a perfect square, so now when I go to square root both sides, I'm just going to put 663 into my calculator. And we're going to round that off to the nearest tenth, so we're going to say 25.7. So use a Pythagorean triple. What you're going to find is there are certain groups of numbers that you're going to start to recognize that always go together when you're doing right triangles. They're the ones that come out to be whole numbers like this, not the ones that come out to be decimals. If you get a problem that comes out to be a whole number like this one, then that means you are dealing with what we call a Pythagorean triple. For example, as I looked at this one, I already knew this answer was 12, right? Because there are certain numbers that always go together that we call Pythagorean triples. Let me show you some of the basic ones. So I'm on page 548 of your textbook, and there's a little chart down here that shows you the most common Pythagorean triples. And it really goes from left to right as far as the most common that you'll see. So the most common one that you'll ever run into is a 3, 4, 5 right triangle. What they mean by this is if one leg was 3 and the other leg was 4, then the hypotenuse would have to be 5. Right, so that's going to go for all of these. The two smaller ones represent the two legs, and the big one has to represent the hypotenuse. This is just one example that they were showing you right here. So this is what we would call a 3, 4, 5 right triangle. And you'd see that it does fit our Pythagorean theorem if you were to plug that in. 3 squared plus 4 squared equals 5 squared. Right, and so that's where these triples come from. So these are the ones that come out to be whole numbers, not decimals. One thing to keep in mind with these is not only do these numbers work, but multiples of those numbers work too. So if you were to take a 3, 4, 5 and multiply all those times 2, you get 6, 8, 10. So for example, if I was looking at a right triangle and I can see that my two legs are 6 and 8, I should automatically know that my hypotenuse is 10 without having to do Pythagorean theorem. So look at this one right here. I mentioned a second ago how I already knew the one answer was going to be 12, right? Because this is simply a multiple of this Pythagorean triple. If I took a 3, 4, 5 and I multiply all of those numbers by 3, well, what do you get? You get 9, 12, 15. So as I look at these numbers, that's how I knew the answer on that other one was going to be 12. Because one of the legs was 9, the hypotenuse was 15, so I already knew the missing value was going to be 12. So what you're really seeing on this page here are shortcuts. You don't have to use these. I could still plug my numbers into Pythagorean theorem and solve for my answer that way. These are just super nice shortcuts. It's really nice to be able to look at a triangle that has a value of 9 and 15, and I just know the missing leg is 12 without having to do Pythagorean theorem. It's a great shortcut. And these multiples go on forever. You could multiply, that's what these are saying down here, is I can multiply these guys by anything I want. So if I could multiply them by 10, and I would have a 30, 40, 50 right triangle. So if I ever saw a right triangle where my two legs were 30 and 40, I automatically know that my hypotenuse is 50 without having to even do any algebra on it. So great shortcuts. So these are the 4, if you look across the top row, these are the 4 most common ones used. So you got a 5, 12, 13. And again, multiples of those numbers work too. So if I were to double these, I would get 10, 24, 26. So again, if I was looking at a right triangle and I saw that one of the legs was 24, I see that the hypotenuse is 26, I would automatically know that my missing leg was 10 without having to do any math on it. So anyway, something to recognize. Again, these are great shortcuts. It's not mandatory that we use these because I can always use Pythagorean theorem instead. But they do save me a ton of time and a ton of work if I understand what these are and if I can remember the most basic ones that you see here. There are others. It's not just these 4. There's many others, but these are just the 4 lowest numbers and the 4 most common ones that you're going to run into. So let's go back and practice a few of these. So as I look at this one, so as soon as I see that this leg is 8 and my hypotenuse is 17, well, I already know one of my Pythagorean triples was 8, 15, 17. And so I already know that my answer for this is 15 without having to use Pythagorean theorem. Now, like I said, of course, if you didn't remember what that number was, you can still use Pythagorean theorem. You can say x squared plus 8 squared equals 17 squared, just like we did on all these, and you can still solve for it that way. It just takes more time. So, again, I looked at this one right here, my 8, 15, 17. So let's try that on this guy. So here's one that doesn't really fit any of those four, but maybe it is a multiple of one of those. Let's see, what did they multiply by this one? So this one is just a little tougher to see, but again, I want you to remember, if I had an 8, 15, 17 right triangle, well, what do I get if I multiply all of those numbers by 3? Well, 8 times 3 is 24. 15 times 3 is 45. So this one must be 17 times 3, which is going to be 51. All right, let's try one more of those, and feel free to pause and give this one a shot on your own. So take a look at this one right here, 7, 24, 25. So let's see how that pattern would work right here. So this is a 7, 24, 25. So if I look at that pattern, well, what happens when I multiply all of them by 4? 7 times 4 is 28. 24 times 4 is 96. So this guy must be 25 times 4, which we of course know is 100. So it's a great way to go when you run into some of these common numbers. Like I said, you can always stick with Pythagorean theorem, and that works too, but it is great when you recognize some of these shortcuts, and you can take advantage of them. All right, let me flip over to the back side on this. Oops. Okay, so on this side, what we are seeing is what they call the converse of the Pythagorean theorems. In other words, if I was given 3 values of a triangle like this, right? So this guy's 10, this guy's 20, this guy's 10 root 3. How would I know if it's a right triangle? Well, we're just using basically Pythagorean theorem to test it. Does a squared plus b squared equal c squared? Because if it does, then it fits my Pythagorean theorem formula, and that would tell me that it's got to be a right triangle. Right? So it's kind of like we're using the formula backwards to see if this is a right triangle or not. So if you were to put these numbers into Pythagorean theorem, right? So take a look at this. So these are the two smaller ones, so those would have to represent A and B. 20 is the biggest number, so he's got to be C. So if we put those into the Pythagorean theorem like this, right? Well, we know 10 squared is 100. If I square 10 root 3, I get 300. And if I square 20, I get 400. Well, as I simplify that, I can see that sure enough, I get a true statement. A squared plus b squared does equal c squared. So because it fits the formula, that means certainly we do have a right triangle over here. So it's a way of testing to see what kind of a triangle we have. So what if they don't equal c squared? What if a squared plus b squared does not equal c squared? Well, then what kind of a triangle is it? Well, there's only 2 other options, right? If it's not a right triangle, then it's got to be either acute or obtuse. So here's the rule. When a squared plus b squared is greater than c squared, it means the triangle is acute. And if they're less than c squared, the triangle is obtuse. Right, so those are the 2 other options if it's not a right triangle. So let's test that on a couple of these guys. And some of these, and this is where it can really help to remember your Pythagorean triples. Remember, a 3, 4, 5 was one of our triples. I already know this is a right triangle because I recognize that this is a 3, 4, 5 pattern. It must be a right triangle. And if I didn't remember that, well, I could still test it. If I look at 30 squared plus 40 squared equals 50 squared, well, 30 squared would be, what, 900? And 40 squared would be 1600. and this would be 2,500. Right? Well, 900 plus 1,600 is 2,500. So sure enough, I know this is a right triangle, because a squared plus b squared did equal c squared. So that one fit the formula. And again, I didn't even have to do all this, because if I recognize that this was a Pythagorean triple, it's already got to be a right triangle. So I already knew it was going to be a right triangle right off the bat. Here's one other thing that I want you to look for, though, as we go forward. I want you to notice the first thing that these directions say. It says, determine which ones could be sides of a triangle at all. So this one, the first part of this question isn't even asking you what kind of a triangle it is. It's saying, first look at the numbers and just determine whether or not these could even form a triangle. Because you can't just use any three numbers, right? Not all side lengths would create a right triangle. So let me give you a simple example here. So I have a pencil, a crayon, and whatever that blue thing is. All right. So could I put those three lines together to form a triangle? Right? Now I often hear a lot, well, yeah, I mean, any three segments can be put together to form a triangle. But let's see if that always works. So if I want to use that pencil there to be my base, so will these guys ever connect to create a triangle? No matter how close I try to put them, they'll never touch, right? So I can't just pick any two segments or any three segments and form a triangle with them, because these two aren't long enough. So here's the rule. The two shorter ones must add up to more than the third side. So when I look at the two smallest segments, like 20 and 30, I have to be able to add those together to more than whatever this number is for it to even be a triangle. Because as you can see right here, if the two smallest sides are too small, well, when I add them together, they're just simply not long enough to create that triangle, because that third side is just too big, right? And so as I look at my numbers, the first thing I want to determine is it even a triangle at all? Before I can even go on to the second part of classifying it, right? If it's not a triangle at all, I got to recognize that first. So first things first, is 20 plus 30 more than 40? And it is, right? Because 50 is obviously more than 40. So, okay, yeah, it's a triangle. So that's the first part. So now that I know it's a triangle, now I can figure out what kind of a triangle it is. So we're going to test it. And again, I want to compare a squared plus b squared to c squared. Right? We're making this comparison. That's what we're trying to figure out. Is, do they equal 40 squared? Are they greater than 40 squared or less than 40 squared? So if I simplify these numbers, I'm looking at 400 plus 900 compared to 1600. Well, as I add those together, I get 1300. Let me just bring this one down. So I know that 1300 is less than 1600, so obviously it's not equal, so we know it's not a right triangle, right? If a squared plus b squared does not equal c squared, then it's not a right triangle. So then what kind of a triangle is it? So as we look at the rule, well, when a squared plus b squared is less than c squared, then it must be an obtuse triangle. And that's what we have in this case, right? So in this case, a squared plus b squared is less than c squared, so I know this guy is obtuse. All right, here's your last two, and again, these are great ones for you to pause and try on your own if you want. Don't forget, the first thing you got to check, though, is whether or not it's even a triangle. So does 6 plus 8 add up to more than 9? And of course, we know that it does, so yep, that's a triangle. What kind of a triangle? Well, how does a squared plus b squared compare to c squared? All right, this is always what we're trying to figure out, is how do they compare? We know that 6 squared is 36, 8 squared, and then 9 squared. So as I add those two on the left, I get 100. We'll bring that one down. Of course, 100 is greater than 81. So in this case, if a squared plus b squared is greater than c squared, I know it's an acute triangle. All right, so those are the three different versions of this answer that you can get. Okay, so they're either equal, they're less than, or they are greater than. Those are the three options. And again, here's the one that you gotta consider. Does 6 and 12 add up to more than 18? They obviously don't, right? They're equal to 18. So these represent three segments that could not form a triangle. So I have to look at those and just say, hey, that's not even a triangle. So of course I can't classify it if it's not even a triangle. So that's something we got to check for first before we move on to that second part.